I would like to discuss the chapter on alternating currents for you today. With respect to CET, this particular chapter, they have been asking 4 questions in the year 2014 and in the year 2015. So we can expect around the same lines. We may have about 4 questions coming from this chapter. These questions are going to be simple application of basic concepts and simple numericals. That is how the questions are going to be. So let us discuss a few important concepts from this chapter. Firstly, as you would know, in alternating currents, the current or the voltage is going to change both in magnitude and in direction. Usually, we are going to represent the current or the instantaneous voltage as a sinusoidal function. So, I is equal to Im sin omega t or Im cos omega t. V is equal to Vm cos omega t or Vm sin omega t, where Vm represents the peak voltage and omega represents the angular frequency, which is equal to 2 pi f or 2 pi divided by t, where t is the time period. Now, we are going to discuss some of the important formulae. Firstly, RMS value of alternating current. As per the definition, the RMS value of a current is nothing but that value of DC current which passes through the same circuit in the same time, produces the same amount of heat energy as done by the AC. And after a derivation, we would arrive at IRMS to be equal to the peak value of the current divided by root 2. And similarly, VRMS value is also going to be V0 divided by root 2. Direct application based questions will be asked from this. And one thing we must be able to remember is that a multimeter, when it is used to measure the current flowing in an AC, it is going to measure always the RMS value, never the instantaneous value. Next, then we have something called as a mean value of AC current or mean value of AC voltage, which is nothing but the average taken over half the time period usually. Because as you know, you will take the average value over positive half cycle. If you take through the complete cycle, then the mean value will become 0. Therefore, it is always taken over half cycle, positive half cycle. After the derivation, we would arrive at the mean value of the AC current to be 2 I0 by pi and the mean value of the AC voltage to be 2 V0 divided by pi. The next important concept that we have in alternating currents is the behavior of the current when it is connected, when an AC voltage source is connected to a resistor or an inductor or a capacitor. Now, when we are going to connect it to a resistor alone, you have a voltage source and a resistor alone, then we will be able to observe that the voltage and the current are going to be exactly in phase. That means there is no time delay between the voltage across a resistor and the current flowing through the resistor. So, V will be simply equal to IR, using which we will be able to find out the value of the current if we are given the value of the AC voltage source. Now, when we analyze the case with respect to an inductor, AC circuit with inductor alone, when you supply the AC voltage in an inductor, the voltage across the inductor is going to lead the current through the inductor by pi by 2 radians. The reason this happens is because, as we all know, the principle of electromagnetic induction, in self-induction, when a current passes through an inductor, when a current tries to rise in an inductor, grow in an inductor, as the current grows, the magnetic field linked to the coil grows, or magnetic flux linked to the coil grows. So, as the magnetic flux linked with the coil changes, there is an electromagnetic induction, there is a EMF which is induced in the circuit which we call as the back EMF, which is going to oppose the cause according to Lenz's law. Therefore, the current is going to take some time to grow in an inductor. Similarly, when the circuit is broken, the current is going to take some time to decay as well. Therefore, current in an inductor cannot change instantaneously. So voltage in a inductor leads the current by pi by 2 radians. Now coming to capacitor, in a capacitor, as we keep charging the capacitor, the voltage in the capacitor builds up. So therefore, the current in a capacitor leads the voltage by pi by 2 radians. Or in other words, the voltage in a capacitor lags behind the current by pi by 2 radians. Now an important analysis will be in an LCR circuit where an inductor, a capacitor and a resistor are all connected in series. Then we analyze the behavior of the circuit. Most important of them is impedance. Impedance is derived to be root of R square plus XL minus XC the whole square, where XL is the inductive reactance measured in ohms, XC is the capacitive reactance which is also measured in ohms, XL is equal to L into omega, XC is equal to 1 upon C omega, where omega is the angular frequency. Now, the most important concept from which we have seen in both the years 2014 and 2014, there have been questions on resonance as well. Resonance is an important phenomenon which is going to be having its application in communication systems as well, in all the receivers and many more applications. At resonance, we see that the inductive reactance is equal to the capacitive reactance. That means XL is equal to XC, which when we derive, we will obtain that omega square is equal to 1 by LC, or frequency F is equal to 1 by 2 pi root LC. We will observe that at resonance, the circuit is going to be purely resistive, which means the impedance that is offered by the circuit is simply resistance R. Z becomes equal to R because XL becomes equal to XC, this factor becomes 0, so Z is equal to R at resonance. Because the impedance is minimum, the current is going to be maximum. Now this is the time at which, or this is the frequency at which the current will be maximum, the power dissipated will be maximum, and circuit is going to be purely resistive. These are some of the factors which we need to remember when it comes to resonance. These are some of the important factors with regard to alternating currents, and as we are going to discuss the questions, some more concepts which are relevant will be discussed. Dear student, we are now going to discuss the question which has appeared from alternating currents in the previous CET examination. It's a very simple question based on RMS value and peak value. A multimeter reads a voltage of certain AC source as 100 volts. What is the peak value of the voltage? Very simple question. We know that multimeter always measures the RMS value of the voltage. So now if you see, the RMS value of the voltage is given to be 100 volts. We know the formula that Vrms is going to be equal to V0 upon root 2. Therefore, V0, which is nothing but the peak value, is going to be Vrms times root 2, which in fact is equal to 100 into root 2. And we are expected to remember the value of root 2. Root 2 is 1.414. Therefore, 100 times 1.414 will give us 141.4 volts, which in fact is the first option. Therefore, for this question, option A is the right answer.